just adding noise at it. Okay, so Langevin algorithm, you can think about it as a gradient descent, or gradient ascent, the same thing, plus noise. And the noise here is there to help you do some exploration. And there are some like properties about this algorithm that are derived. For example, if you keep this distribution here fixed, meaning that this P here is, if you keep running this algorithm for a long time, you'll end up into a stationary distribution for your walkers. And this stationary distribution is precisely this P of X. Okay, so the score here is kind of like a principal thing here. The problem with this, the problem with this particular algorithm is that it cannot actually solve this density here. Now, I mean, what I've said about like it solving a distribution only works if it's actually a unimodal distribution, but here I've given you a multimodal distribution, and this algorithm will not solve this problem. And the reason will become is perhaps simple. So for example, here just the first component, Brown in motion, just adding noise. It's a random exploration of the space. Naturally, just the noise component itself is not able necessarily to find good solution. I mean, that's not super surprising. So if you add the gradient of this thing, and okay, so like actually, so I know you guys are all JAX people, so but wait, do I have it here? Oh. See, I was working on making all this clear, and now I have to work from this. No, it's not here. It's actually very, very easy to, okay. Let's just do it by hand. So in Torch, the way you would compute this, naturally, you would use automatic differential, like automatic differentiation to get this. So for example, if you have access to a log probability distribution, so here I believe I call it yeah. So I call it like this. Then it's very, very easy to get the score itself. The score is just the gradient of the log probability. So see, like ChatGPT is doing all the work for me. Very nice. So in Torch you would do this. You would call this board. You would do it like this. I think it's similar in JAX to some degree. Yeah, and you would be done, and then basically the way you would write this kind of like Langevin algorithm over there, you would do something like okay, so like the first thing obviously is you would sample this Z here, which is kind of like Brown in motion component. And you would do one step, which is basically saying I'm gonna take a step size of a step size of epsilon. I'm gonna take a step in the direction of the gradient. And I'm gonna add noise here. And that's basically it. And then if you just pick point randomly in that space and then you follow these trajectories, what's gonna happen is that they're gonna fall in the mode that's nearest to them. This is what I mean when I say this SDE does not solve this problem at all. Because what you would want, if you really want to sample from this distribution, you would want this walker to jump between the modes. Now, you might say, okay, but I don't typically encounter a situation like this. I have my nice problem that has a single solution. The problem is when you go to very high dimensions, which is where these models are very interesting and useful, what you'll encounter are multimodal distribution. You have like no choice to deal with those actually. And so like algorithm like this that just try to maximize a simple function will fall toward a solution, maybe a local minimum or maybe a global maximum, but it's going to fall toward the closest. It's very hard to change this behavior. Okay. Okay, but okay, so it doesn't solve the problem necessarily, but oh, I wanted to do something which is kind of interesting actually. I'm gonna go back here. did I do that? I think, did I do it? No. Okay, this is why I define the distribution. Now, like, you don't have to like, so all I'm gonna do here, and I guess this is gonna be a question for you, what's gonna happen? So this is the distribution that I created. There are equal weights each month. Okay. So if I change the weighting between these things, so suppose here instead I do I'm gonna pick some weights. So like for example, let's say I do I do one that's like much less likely than the others. Okay. And then I'll just normalize this. And I'm gonna just give this here. Okay. Okay, so if I do that, now there's one mode that I sample much less. So here's a question that I'm gonna give you, which I think is interesting. And the score function is like just this gradient, like I can probably just pull it out here, but it's just this gradient of this log probability, right? What do you think is gonna happen? Is this are the vectors gonna change, or are they gonna be like bigger for the modes that are more likely and smaller for the mode that's less likely? What's gonna happen?
I would guess that for the smaller mode with this less probable, the basically the vectors pointing inwards would be much, much closer, and the other ones would sort of fill the rest of that space. So meaning it's less likely to be sampled, I guess.
Okay, I mean that's an interesting, but remember what I said, right? There's one component that's gone from the score, which is this kind of like global property. It's the same thing. What did like is it a bug? Does my code work?
That's not what I expected.
This is actually like the right thing, right? I call it this. Now,
Hmm.
but why does this happen? Now, but it goes the first thing that I said when I started. So this information about, I mean, I can maybe, I don't know if I can do this like super fast, but um
Because you haven't changed the sigma on the Gaussian, you've only changed the normalization
but I've changed the weights.
gradient.
Right.
Yeah,
But you're right. I haven't changed the normalization, but still I've changed the weight.
Yeah, but you're not differentiating the Gaussian, you're differentiating its log.
Mm-hmm.
So that normalization factor is gone.
Exactly. The normalization factor is gone. Like the information where this is stored, where like the amount of weight between like each modes, this information is encoded in the partition function. Like if you know, and this part is completely gone because the score is like purely a local function. So actually, when you have the score like this, it's even worse because if your modes are not equal, this information is lost. But not everything is bad. So what we'll see is that somehow this can be recovered, right? Okay, but before I go into like trying to recover this, let's try to fit the neural network. Okay, like just like super naively again. Like I'm not even gonna try to do anything fancy. So now all the code is somehow hidden here. So I'm just gonna like pop it up a little bit. So what I'm gonna do is I'm gonna say, okay, let me just take this score that I have, which it's a bit dumb what I'm gonna do because I already have the score. Why do I need to fit it with the neural network? But for the purposes of this presentation, I mean, I'll do later the actual thing we do with data when we don't have this, we don't have the true score function. But here I do, so I'm just gonna play with it. So I'm gonna take this and I'm gonna compute a loss, which is literally gonna be take this kind of just take this model and try to match the true score. That's it. That's all I wanted to do. And I just need. And I think ChatGPT is trying to do something not right. Right. Okay. So just take this loss function. Sample from my distribution, compute the loss, and maybe I need this. And, okay, I think it's fine. So just do a bit of machine learning. Oops. I think my computer is struggling a little bit. I need to define this. Okay. So this is typically very fast. I mean, this is very, very small and trivial problem here. So I fit the network with points that I just sample from the distribution itself. I reach kind of like a loss of 0. Great. If I run this, and then it's garbage. I have perfect information. I'm sampling from the distribution, right? So like the loss that so the loss that I'm doing is like just mean squared error. So sample from P of X and just try to match the actual score. And it's pure garbage. Now, does anybody have an idea why?
When you say match the score, how are you getting the score from just samples?
Well, I'm not using samples. I'm using the actual
Are you
I'm
using
doing like I'm taking the actual like analytical solution and I'm trying to match it. I'm gonna do score matching with samples a bit later, but I just want to build intuition here. Even though I have perfect information here, it's still garbage. And the point is, I mean, okay, but it's a question. Why is it so bad?
Is it because it's sort of like multimodal, not quite multimodal, but there's unique areas that sort of look like it's trying to create one converging solution?
I guess, I mean, it's trying to.
Can you scroll up to the code again as well?
Yeah, I can show you what I did, right? So like what I did here, oh, and remember, like the score here is an Rn to Rn. So here I have 2 dimensions. So I need two dimension for input, 2 dimension for output. I just chose kind of like one hidden layer. I mean, the activation doesn't really matter here. And like 10 units, like it's kind of like super simple here, what I've chosen. And so this is just a function that takes a vector of 2 dimensions, spit out another vector with like 2 dimensions, right? And the last function, I'm just targeting this true function, which I should not have access to normally. Like it's perfect information. Now, the reason this doesn't work is actually because, okay, so like look back here when I was sampling, wait, where is it? Okay, there's only points here and here and here and maybe some there. There's never going to be points in those empty spaces ever. The network never sees those. So whatever the network does, it has to somehow extrapolate, right? It's out of distribution. Never seen those points. It has to figure out what's the right score there, which he has no clue, right? Because like the loss function, the way it's always constructed is sample from your data, whatever that is, and with your target there. And so like if you try to do this even naively, like let alone trying to do this with samples, just like this, it's bound to fail. So okay, so now like I've introduced like a bunch of problems. It seems like kind of hopeless, but there's one cool idea that solves literally these 2 problems. Okay, like, so intuitively, what do you guys think we should do to like help the network learn these places where it doesn't see points?
Well, don't sample from the distribution, sample from some, broader distribution.
Exactly. So the solution to this problem is literally to, introduce annealing, introduce temperature, anneal the distribution to make proposals that are going to propose points much farther out. And this is especially important for high dimensional spaces like images and everything else, because images, they, define a portion of the space of all images that is so tiny compared with, the entire space that images could occupy. So like for a high dimensional space, what I've just shown here is magnified 1,000,000 times. It's a problem that's much bigger than this. And the problem for all these things is, okay, so what we want is not just to have points from the distribution itself, we want points around it too. So simplest thing, we're gonna add noise. Just add noise to your data. Okay. And okay, so I'm gonna skip the math because I don't necessarily want to, do this, but like for this simple problem, I can solve, adding noise, I can solve what this means at the level of the distribution analytically because everything is Gaussian, everything's trivial. So I know what the solution is for like any kind of like noise that I add, what the resulting distribution will be. And so I can show you here, so on the left, if you don't have much noise, you have these kind of like samples that, are very concentrated on the modes. But as you add noise, the points start to fill more of the space. Now the question is, okay, so again, I'm gonna do now I'm gonna do something simple again. I'm gonna take this distribution that's analytic. Okay, I'm not necessarily gonna run it because I only have 20 minutes. I want you guys to interact a little bit, but because running it takes a bit more time, but I can show you yeah, okay, so the architecture is just slightly a bit more complicated because here what I need to do is not just target one distribution. I need to target all the distribution that I've added because T here indexes a set of distribution now for any set of noise that I'm adding. And the cool idea is not just to add one set of noise, is to add like a lot of them up until your noise becomes dominant and covers your space. And you'll see why. But so if I do this, now I need to condition my neural network on this T parameter here, which labels which distribution I'm targeting. So the neural network needs to be aware of this, otherwise it's not going to know what to do. Then you have to give it T. So here I kind of like show you how, you can do it for a simple network like this. You kind of like, the trick is to project it with like some linear layers like this, concatenate to X, and you're on your way. Another trick of the trade is to, to make this more stable is to reparameterize the neural network, just divide by sigma t here and weight this loss by sigma t squared. Trick of the trade, but this is how it goes. And okay, so you can fit this. And okay, so the results are interesting. They're a bit better. Now, what you will see is that the score, especially at high temperature, it's got a very easy job, essentially. At high temperature, the distribution is simple because you've added so much noise that the details of the distribution have completely disappeared. Now you have like basically a single Gaussian. The neural network can approximate this super well. And then it still does a good job as you lower the temperature. However, it's still bad. Typically, it's still bad at 0 temperature. And for images, especially, it's even worse. Like it's terrible at 0 temperature. The neural network does score, and you have to train it for days because it doesn't have to train to learn a single distribution. It has to learn the set of distribution. Typically, it's going to be good around the middle because this is where the most complicated stuff happens. So here we kind of like missed a bit the target, but for a diffusion, sometimes you would train maybe much longer and to get those score right. Okay. Are there any question about this so far?
So is noise then just like a hyperparameter that you have to tune depending on how your distribution looks?
Okay, good question. So the thing that you tune is the schedule itself, typically. So the sigma t. So there are tricks to tune this. So typically you want to add enough noise to wash out all the details, not just about one image, but about the whole distribution of your data set. Just adding noise, now as it turned out, just adding noise is a bit tricky because, for bigger distribution, it turns out you have to add like so much noise that it becomes computationally like problematic to deal with these large numbers. So there's another trick typically, which I don't go here, which is to rescale the space as you add noise. If you combine these two, you can make your space shrink to 0, and then your noise just goes to 1. I'll show you later, the package that I have, which I don't necessarily introduce here, but there I have kind of like an interface where you can just kind of like instantiate a score model with a schedule that sort of makes sense, and start playing with fitting distribution and problems. But yes, the first thing you have to do is tune this noise schedule such that the idea is just that it's going to destroy, it has to destroy all the information about your distribution. So here, kind of like adding noise up until sigma equals 2 makes sense because my modes were separated by a distance of 2. And that's how I picked this sigma actually. I just picked the maximum distance between modes. Actually, probably missed it because it's square root of times 2, whatever, but like for the diagonal, but it's good enough. Okay, so and then connecting this then to diffusion. Okay, so now the idea of annealing is important for sampling. Now the cool idea is that when you've introduced an infinite set of distribution like I just did, I didn't just introduce like 10 or 100, I introduced an infinite set. It was parameterized by a continuous parameter. When you do that, you create, underneath that whole thing, you create the stochastic differential equation, meaning a continuous process of changing a distribution while adding noise. Now, I'm not going to go necessarily in detail about stochastic differential equation, but remember, a stochastic differential equation is essentially just like Langevin. Okay, so it's just like Langevin, the Langevin algorithm. You're adding noise while following a gradient. Okay, so here what I'm showing, but the cool thing about stochastic differential equation is that they have these like two sides. So when you were training, we were adding noise. We were starting from a point at x0 and adding noise up until some other point. That corresponds to, there's a corresponding stochastic differential equation to that process. And you can follow it, meaning that if you solve this little thing here, actually, do I have the code for this? Yeah. So it looks a lot like the Langevin algorithm in the sense that, or actually just Brownian motion. So you're taking x and you're just adding some z here. Now, instead of adding some epsilon, I've separated into a GT, which accounts for like some time change and some time discretization. Turns out you need to square root it, but okay, that's not a problem. And if you solve that dynamic, what happens to the point is they follow these contour lines of the distribution that we solved earlier just by solving the convolution. Okay, so this dynamic process of changing the distribution corresponds to a stochastic differential equation. Okay. And then what's cool is that you can reverse time. A bit like you can reverse time in an ODE. Now, when you reverse time in a stochastic differential equation, it's not the same equation that pops up, right? You cannot just reverse time for a stochastic process and hope to get the same trajectory, but you will get the same probability distribution change if you add an extra term, which turns out this extra term is just this score here, which we're spending our time learning. Okay, so this extra term that pops up when you reverse time in a stochastic differential equation is the score which we're trying to learn. And if you solve this dynamic, so I think I have the code. It's a bit hidden, but like it's this guy. Okay, so this guy here is basically the same as above, right? This brown in motion term. So Z is pure noise. It's so ran ends like random normal distributed like X, so same shape. G is this factor that that scales the noise, and you have this dt. Now dt now in this one is a negative time step, so I have to just make sure I don't create like imaginary number in there. And you have this term, which is a bit like the Langevin algorithm, where you kind of like have this step, and this g here is squared the same way that like epsilon was epsilon was square rooted here, and then there was just epsilon kind of like naked here in the Langevin algorithm. Here it's kind of like g squared and g, the same relationship really. And when you solve that, what's cool is that now when you initialize this process at pure Gaussian noise, which was the thing that we created when we destroyed all information, and you solve that process where every time you take a step, you just do this term, and this thing goes back to the distribution you started from. And if you had different weights for your modes, they would still work. And the reason is like they would actually have the right weights. And the reason is because the information that you lost when you were constructing this score, this global information, is recovered in the annealing procedure when all the modes merge. That's kind of cool actually. But okay. So okay, but now I've been doing stuff really, really dumb, right? Like what I've been doing here was like always using the true score function. Now, what I need to do is show you, in order to use this in practice, I need to show you how to use this just given samples. You don't have P of X, so you cannot just compute this gradient. So what do you do? Once you have the score, all that I just said about like the stochastic differential equation, this is how you do diffusion, right? Like you just stick your model instead of like the true score here, you just stick your model in there. But now you have to just approximate this thing, right? Okay. So the way to do it is actually kind of interesting. So and I've had many discussions about this. So you have a data set of samples. What is this? Well, a data set of sample, you can say, okay, well, I'm going to construct a distribution around this. I'm going to just say that each sample is a Dirac distribution with probability 1. I mean, that's the choice. It might be it might not be like kind of an elegant choice, like but in the limit where you have lots and lots of data, this Dirac distribution will represent any other distribution. So only in the limit where you have lots of data is this choice valid. Otherwise, and there's kind of like an interesting point also as to why diffusion models don't just spit you back out their training data, because here the way I'm constructing the score matching algorithm, I'm constructing it with a procedure that should always come back to my training samples. But that's maybe a question for another time. So starting from a Dirac, I should only get back those samples if I solve this process exactly. But starting from a Dirac, it's very easy now to convolve that distribution the same way I did before, except like now it's even easier because convolving a Gaussian with a Dirac is like very trivial. So I get all my PTs now again from a set of samples. Okay, great. Now, okay, but it's still not fun, right? Because the score is basically the gradient over, I forgot a log. Forgive me, I forgot 2 logs here. Oh God. The gradient of P is definitely not the same thing as the gradient of log. This is very not the same, because the gradient of P keeps the global information, the partition function. But if you put the log, then it disappears. Okay. So it's supposed to be a log here. So this PT of X is still not fun because you have to take a gradient over the sum. Now, as it turns out, there was this paper from 2011, way before, this thing blew up in the beginning of it, 4 or 5 years ago. We realized that you could just do integration by part, roughly speaking, and then just condition this score here on x0. X0 meaning a point from that original distribution from your data set. And now this score here is trivial. Okay, I should probably fix this. This score here is trivial. Let's see, log. Because if you condition on if you condition on a single point, this sum collapses and you're left with a single Gaussian, right? So now your score is very easy to evaluate. And if you do it, I'm missing another log here. Wow, I missed them. I missed all of them. And okay, here. So if you do that, okay. Wow. Stuck.
Sorry, I don't read LaTeX.
What's happening? I don't know why it's so slow. Ugh. Wow. Okay. And if you do that, if you solve it, now I've expressed it in terms of a z. And basically, like the way you need to think about it is that you can always reparameterize a Gaussian, so instead of like sampling from this specific Gaussian, you can say, I'm gonna sample from, I'm gonna take the mean and I'm gonna add a z, I'm gonna sample a z vector from a pure normal distribution. I'm gonna multiply by sigma t, and I'm gonna add that to my xi, and that's gonna be a valid sample from that distribution. That's a trick that we always use in machine learning. That's the one we used before when we were kind of like adding noise, right? Do I add it here? Oops, I went too far. Basically this, right? This is kind of like how you sample from Gaussians, this normally. So, okay. So in terms of that z, you can prove that this is correct. Now notice the minus sign here, and it still boggles my mind that people get the sign wrong in the loss function to this day. So your loss function, the way it should be written when you write it correctly. So now, okay, so now this loss function here, unlike the other before, I'm not going to use the true score function. I'm going to use samples, right? So here I sample from the distribution, like I was doing before, right? I sample at time randomly from 0 to 1, which is basically just choosing the temperature at which I want to evaluate this thing. Sample a z here. It's just the weight factor, which I choose to be sigma t squared. Again, like trick of the trade, but okay. Get that xt here, which should be good. So basically just do, I guess, it should be this. Okay, that's a bit simpler. Okay, so then I get my xt like this. Now, what's cool is that using this, now I can just say, now my loss is, okay, so take the model. Oops. Okay, my target now is this minus z over sigma squared minus right, like this z here that I just sample. This is what solved this for. And then I can do minus target. Now, for some reason, there's still, to this day, some reviewer that comes to me and they're like, do you have a problem with your sign? Because typically I just write plus z here in my papers. Now, it is what comes out of the math. Okay, I'm sorry. But some people still use the minus sign. And then what they have to do is they have to do minus their neural network to get the score to stick it into their SD. It's crazy. Okay, whatever. So minus target. Okay, and so this is the score matching loss that you get. So now no need of any true log probability. You can do this with like images. It's so simple. Like it's literally just that. If you remember just kind of like this simple procedure, you can just apply and you can apply this to any data set. Now the tricky part with like most data sets is you have to create big architecture because there's lots of information to encode. So you need lots of parameters and you need lots of training. That's the only tricky part about this thing. But if you're in lower enough dimension, typically like smaller neural network will work, like this one. And so if you do this, another thing I need to mention. Now here, look at this loss curve, okay? This doesn't go to 0. Don't think that I'm overfitting. It's like literally impossible to overfit. Okay, so if you see a curve like this is good. Just keep training. Just keep training. Like this is kind of like the secret of it all. Okay, just keep training. In my lab, I get this question all the time, and I need to remind them that, okay, what you've learned about machine learning, overfitting, all that stuff, just forget it. Here, close your eyes. Just go train that thing until they kick you out and you cannot use the GPUs anymore. And if you train long enough, then you can stick that score in that SDE, and it's going to just do that thing again. Because here's the thing, a neural network is a universal approximator of a function. And here we have one function that okay. So these two things are completely equivalent, meaning that these two objectives here are equal up to a constant, which means that if I take a gradient relative to them with respect to the parameters of that S, I'm going to get the same function out. Okay, so this thing really learns this gradient that I was trying to learn up to some error, some approximation error. If you make your neural network big enough, it's just going to do a better job at finding out this thing. So you want, like, literally, you want the biggest network, and you want to train this for as long as you can, because you just want that error to go down. Now, like, it might not look like it does, like it doesn't look like it goes down, right? But I mean, there are some things that happens during that phase of like not going down. The network is still learning. This is crazy. Like I can train like this where my loss doesn't go down for days and I still see improvements. Okay, this is amazing. But the point is just, this is so easy because you have a universal approximation function approximator, you have a principal objective that just target a simple function, and you just fit. And you don't have to worry about anything else because this thing is going to cover all of space. So there's no such thing as out of distribution. You've literally covered all possible points in your, vector space, depending on the type of schedule you've chosen. Okay, so that covers kind of like, that covers score, like what I wanted to show for this. I didn't go into inference. Obviously, this is what I do when I use these things for inference. And there it is, like a bunch of caveats and other things you need to worry about. But for if you just want a model that just generates stuff for you, this is basically this does it all. I used to have another plot here that showed that the score again is very bad at 0 temperature. Oh yeah. And remember this, right? The score at 0 temperature is really bad. Don't trust it. Don't just think that you can put a t equals 0 in there and have a good score. It doesn't work. All right.
Cool. All right. Thanks for that, Alex. This has been really awesome. So we all want to thanks, Alex. So thank you very much. That was great. This is like, yeah, really detailed, like from the ground up. Like, I've got confidence that most people here would be able to actually go and actually play with these models. Yeah. Do you want to provide us a link as well to your repo?
Yes, I'll do that. I was
to run to my next meeting. Sorry, but that was awesome.
Yeah.
all right, okay. Sounds good.
Yeah. You can send a link to me, and I'll collate some of these resources and put them together.
Yeah.
So, yeah. Do we have any questions? Or yeah. All right. If people are still thinking,
Nice.
I did have a question. It
Yep.
was on the changing of when you take samples in their direct deltas and you change it to a continuous distribution, and you sort of get to choose the size of the convolution or the size of the Gaussian that you can involve with. How do you choose that size? Is it something like you choose it such that samples that you've maybe kept out of training are still represented well, or is there some other technique for this?
So the idea here on how to pick that is extremely simple. So what you want is, okay, because okay, so here's the thing that these diffusion models do. So when you start from a distribution here where you have your four modes here, and you end up with a single Gaussian, the goal of this procedure is to go from a distribution that's complicated, that you don't know how to sample from or even describe. So say like this four Gaussian, like say this four Gaussian was like super complicated. To what the goal of this noising process is to destroy information such that you end up into a distribution that is extremely simple. Now the point of it is when you end up in that distribution, well, okay, so you can describe it with a simple Gaussian, so you can just draw points. So you can always, so when it's time to reverse, so when you go to reverse time, you actually start from there. So it better be simple because you're gonna have to sample from it. So you have to add enough noise until you've reached that point where the distribution, like all these points, they're just gonna converge into a single Gaussian. And then you're gonna draw these points and you'll have enough time to reverse that. So how do you pick that width? Generally speaking, the way to pick it, so here I picked 2 because these modes were like, on average separated by 2. So what you want to do is like, if you have a data set, for example, you want to draw pairs of points, compute the distances between these points, just pick the maximum distance, that'll tell you how much noise you need to add. For some data set, when you do that, the number is going to be humongous. So what you have to do is do that other trick that I mentioned, which I'm not touching here. So this process that I've described is called variance exploding. SDE. Variance exploding means I need to add more and more noise until the variance just explodes because, if your data set, like if I just pick these modes and I draw them to infinity, I would need to add infinity amount of noise to like destroy that information. So you can combine this adding of noise process with another process that's a bit more deterministic that rescales the space. So, I mean, the way to describe it in terms of math is to say, so everything is described typically, wait, where is it? Okay, so like this little equation here, I'm sorry for doing this. I hope it's not gonna break. So we call this, we'll just. Okay. So this little equation here, oh, you can see it on the right, perfect. Okay, so this, like what describes the whole SZ is what we call the perturbation kernel. So the perturbation kernel is, the probability of getting a point xt, so like at some temperature T, given x0. Okay, so this for diffusion models, this will always be a Gaussian. And the point of like, the reason why like these diffusion models work so well because we pick a very nice noising process, which is generally described by a Gaussian. So Gaussian here. And then, so the trick is to add this kind of like new function. So on top of having this sigma t, you have this mu that also rescale your space. So this mu will start at 1, meaning that like at t equals 0, you'll just recover your geometry that you had. But it's gonna go to 0, meaning that if your points were very spread out, which can happen. For example, I do high dynamical range imaging with these diffusion models, and so my dynamical range can have like 10 to the 5 range. So if I compute distances, I get numbers like 10 to the 12, 10 to the, obviously I'm not gonna add 10 to the like a variance of like 10 to the 12. Like that makes no sense. So I have this mu here that just rescale the space and like it goes to 0. So basically it won't affect my so the information will be destroyed faster, if you will. And in fact, like when you add this mu, it becomes super easy. You don't even have to think so much about the hyperparameters anymore because this mu does so much work for you that basically the same hyperparameters always work. So so like the default on my package for what I call is the VP SD for variance preserving. The default on my package for this basically always work. At least for all the problems that I've used them on. But yeah.
Ooh. Do we have any other questions in the audience, or if not, I might ask. I'd love if you showed the that galaxy deconvolution result with the HST versus JWST. I still love seeing that all the time. It's so crazy. If it's easily accessible, yeah.
I think. Oh yeah, they proposed this thing. I think my computer is very slow. I don't know why.
That's probably a sharing.
But let me stop share for a second. I'm gonna see if I
Yeah,
like.
yeah, that's fine. Yeah, so for context, Alex has built a lot of diffusion models for galaxy deconvolution in HST. And yeah, so now the JWST is up there and has much better resolution and all that. There's been some nice validation of some results that were potentially spurious until we could actually go and confirm them. So it's a really nice result. Did Alex drop out? Okay. I assume he'll jump back in a minute, unless his laptop crashed or something. There we go, he's back.
Okay, my bad. I'm back.
Oh, good.
Okay, I got the paper. So yeah. Okay. Okay, so same thing that we've seen, except now I just crank up the number of parameters to like a few tens of millions, make a big network, train it for a few days. And I use an extra trick, which is I want to sample from the posterior, except the problem is my data is super messy, right? So my data, which you see on top, looks like this. And so typically I would use like a Gaussian likelihood, except here there's like these cosmic rays, there's all that stuff. So I want my forward model. I want all the physics that I know from the telescope, the PSF, aberrations, dithering. I want all that stuff. So I code this in differentiable way because remember I need to take scores, right? So I need gradients. But I cannot just build. So what I do is I build so I have this big data set of galaxy images. I just train a score network on this. That becomes my prior. Now to sample from the posterior, I need to take that SDE that I was talking about, and I need to add an extra term, which is supposed to represent the likelihood. Now there's some caveat here where this is a bit illegal mathematically, but still works. The only thing that I need to do is make sure that the likelihood represents the type of noise that's going to be in my data. And this noise here has these kind of like cosmic rays. So what I do is I train another score network. This one, I pick a big data set of just noise sample from Hubble Space Telescope. Right. So instead of galaxies, I feed to my SVM noise. And this becomes a likelihood. When I integrate it, when I take my forward model with it, it becomes almost equivalent to the score of the likelihood for, you know, Bayesian inference, except at all temperature in a diffusion. And so what I do is I just take these two big networks, and then I just solve the stochastic differential equation. I just start from pure noise, and I just wait until I get samples that are supposed to be consistent with my observation. The way I know this, two things. I expect the posterior sample to look roughly like a galaxy. So here, this is actual data from HST. I've picked kind of like the most horrendous, disgusting, low surface brightness galaxy that I could, you know, take. Well, I mean, you could probably pick worse, but you know, okay, whatever. Like I picked those. So, and I solved this reverse stochastic differential equation to get an image like this. This is resolution. So this is 256 pixels on a side. So this is about, you know, what, 50,000 dimension, give or take. So, okay, so I solved this thing in 50,000 dimension. And the way I suppose that this is good is I look at the residual, meaning I take it through my forward model. So I apply all the instrumental effect, and I take the difference with the observation. Now I have 4 because I have 4 ditters. And what should be left if I've really extracted all the signal and my likelihood is happy, my likelihood, which is all these noise, only thing that looks like these noise samples that I've trained on. And indeed, this is what I get. Like basically like this thing of the galaxy here, everything is left. And this thing has not broken, even though there was these nasty cosmic rays. Like normally you have to mask them, right? Because this is not Gaussian distributed. But here, I literally don't care what's my observation because I know what noise is. I've trained on it. And then, okay, so this is good. And then I can go and take even worse observation like this one. But this one, what's cool is that this was where James Webb sort of like, there was this like the first deep field of James Webb. They would compare it with like Hubble, and they would show that James Webb would be so much deeper. And here you can kind of see it, right? Like if you drizzle, meaning you combine these dittered observation together, and you get something like this. It's a bit deeper than single observation, but definitely not as deep as the reference. Now what's cool is that if I apply my techniques, now it's not perfect, but I recover many, many, many of the features that were completely hidden in here. I've removed the PSF, so like basically this is super sampling the observation. I recover kind of like these fire alarms that in there that were completely blurred out here. And you know, this works pretty well on like let's see, other observation as well. So I mean they're all kind of like back there. But the point is, I don't just get one image, right? I also get a full posterior. So I can also like compute uncertainties. I can compute, you know, so like the one above I was showing the median, right? So I would draw 200 samples from my stochastic differential equation, and I would combine them into a median, and that would tell me sort of what are the consistent features that I consistently recover from this algorithm. And this tells me like which one I should trust more than others, right? Like if you know, take this for example, I get 2 posterior samples from this observation. Now, you know, you can see maybe like, oh, is this kind of like a star? Is this an actual feature? Like, no way, like, you know, this thing here, you don't see it at all in observation, right? So like, is this how like completely hallucinated? Maybe it's below the noise level, that's for sure. When you draw another posterior sample, it doesn't appear again. So you say, okay, well, you know, it's maybe likely a little bit, but you know, I cannot just put all my money on the fact that this feature might be there. So I have uncertainties on, you know, morphologies of these things, even below the noise level, right? But for example, like this feature here, like this fire alarm here, I mean, it's probably definitely there, and you can see like you can see it a little bit in your observation. So the model just consistently recovers it. And when you take the difference, like, you know, it is extracted all that signal, right? So, all right.
Yeah, awesome. I just love seeing the image. It looks basically as good as the James Webb image that you pulled out of Hubble. It just blows my mind every time.
Hey, Alex,
when you take the median, are you taking the median of every pixel value?
Yeah, pixel wise, right? Yeah, exactly. I mean, I don't necessarily know how to get, I mean, I could compute the mean as well, but I don't know if I could get like other moments that take into account like the covariance. I didn't try to.
Yeah. Yeah, like what if you have long tails on some of your like pixel distributions and that sort of biases
This
I guess
is
median's
what-
more robust to that, but
Yeah, I take the median, and when I report uncertainties, I report the percentile range, which is more robust to these like crazy outliers, which I do.
okay.
I do sometimes have like crazy things which I'm still trying to fix. Like, some odd percentage, the score just goes crazy and blows my posterior samples. This annoys me.
Yeah.
Just
Do
but
more training.
do more training, or like
Add more layers.
it's also it's so simple, right? Or but
Exactly.
but it's also like the training data itself, like, I mean, now my prior is the training data itself. My best recovery on this, okay, so this may be an interesting thing. My best recoveries on these posterior samples is from observation. Now, okay, it's probably not surprising, right? Like if I go to simulations and I try to train these core models, these simulations are not good representation of reality at all. And you can see it when I take, so probes here is from real data. The probes is real data, and this skirt here is from simulation. So if your prior assumptions were purely based on simulation, you would miss a lot of these features, because simulations just don't have, the required resolution or like the correct physical, like well, not necessarily the correct physical model, but like the correct resolution to run things such that you could see consistently these features in the simulation. You need to go to observations to see high quality data. Like there's information in observation that is, I mean, this is not surprising to all you guys, but there's lots of information from observation that is still not captured in simulations. We don't necessarily know how to bridge that gap. I just know that if I have to train my priors, I need to bring some observation in the mix. I cannot just take simulation as my representation of like my knowledge of reality, because I actually know more.
Yeah, cool.
And that's where all the physics is, right? Difference between the simulation and the observations.
Yeah.
That's where the fun begins.
Yeah, but I also
Yeah.
meant to ask you about the drizzle as well, because like as you mentioned, drizzle is not a probabilistic thing, right? It doesn't give you posteriors. So sometimes what I've seen in my field of interferometry is that based on the level of, so you showed your median images, right? But you also have a noise sample, right? I guess, or some estimate of what the noise looks like.
Of the
or what the posterior of the noise, right? Like what the noise could look like.
Oh, you mean like, yeah, like in the observation, you mean?
Yeah. Like all the cosmic rays and all of the other sources of noise. Like you essentially know what that component of the image is as well, right?
I mean, I don't know it as well. So I mean, when you go into input, right, like you don't, and this is funny, like we make fun of this all the time, but like people, for example, in like more observational kind of like fields, they're gonna say, oh, I want to remove my noise. But the problem is like, okay, your noise is much higher entropy than your signal. Okay, so like if you try to remove noise, you're just starting from like a losing ground. Like you need to remove what's like low entropy first. So like when you say, here's my prior and here's my likelihood, you're saying, okay, whatever goes in my likelihood, which I call noise is just a giant basket of like all the things that I don't understand. And the prior models, the low entropy signal that I'm interested in, right? And this produce all these things. So
yeah, but what I meant to ask you about that was kind of like you have this big bag of noise, right? But you can actually use that to infer how much information still exists in the original data.
Exactly. Yeah. So this is residual, right? Because this is information about like exactly how much information is left to extract.
Yeah, so like in my field, sometimes what I see is that you blur the reconstructed image intentionally to get
Right,
rid of details that you shouldn't be able to have inferred in the first
no,
place.
I complain about this all the time. We have a paper on interferometry, like yeah,
Oh, okay, perfect.
yeah. Oh man, it
Yeah.
drives me mad. Like the fact that they convolve the result. Oh man, it's crazy.
Yeah,
Okay.
I agree.
But it just tells you like they're not confident in their algorithm at all. They're like, oh, it's probably bullshit below that scale, right? But there's actually information. Okay, I'm gonna show you information below that scale right now. Like we actually did the same thing on ALMA data. Now here it's easier because I don't have to deal with cosmic rays. So like I can just take my Gaussian likelihood and I'm happy. But wait, PDF. All right, let me share my screen. Okay, well, we have this comparison with Clean actually. Where is it? All right, below that. Okay, so clean is exactly what you just said, right? They blur their observation because they don't trust it. So obviously, so clean, the way it works, they just draw points on like a continuous map, and then like I don't know, and then they just like randomly place like they place their points until like it starts to fit better the observation, and then just you convolve with a Gaussian on top. And this is what you said. It's like it's got this like Poisson noise kind of thing, which kind of like comes from these points, convolve, right? Now MPOL is a bit better, but here what they do is they do like Bayesian inference a bit like us, but they don't have they don't use score-based model. So what do you do when you cannot model your prior with a flexible function? You revert back to the simple things like Gaussian. So they assume a Gaussian distribution on their flux, which does okay. But if you do have a Gaussian prior on your flux, there's a lot of noise from your observation that's going to leak back into your solution because your prior allows it. If you do like us, and here, okay, here's a crazy thing. Like, I don't know, here I'm starting from an SBM that was trained on galaxy images, not protoplanetary disk. I took the same network. I did like 3 papers with the same network, the same bloody network, just trained on like 2000 galaxy images. Okay, and I'm solving protoplanetary disk with it. Just because there's like it's a better prior than Gaussian. And I recover some structure that is just completely blurred out in traditional methods. And I give you uncertainties on top of it, right? Like I can compute the median, but I can also tell you, okay, so what are my uncertainties on these flux? I mean, pixel wise. It's kind of interesting actually. Like this one is kind of fun. And if you go here, okay, this is kind of cool. So now here, like we've been running this thing for a while. So now here, same thing as before. I have this kind of like probes. So from observation, and here, I don't know if you can see, but like, we don't see super well. Okay, we're like here. Okay, so here we're starting to resolve structure within the disk. Okay, so now there's a question. Okay, so like, is this okay? Like, or are we completely hallucinating the structure? So these other priors from simulations, they don't do as well. They actually have a smooth disk, and they kind of like, which you might expect from the clean solution, whatever. But here we're starting to resolve within the disk. So now so we forgot to plot the little ellipse that people usually plot here to like give you a sense of the resolution of the observations. But we certainly don't convolve with that. That would be like we would be blurring all that structure. So like, is this okay? Like, is this actually like we don't know? Like here, when we take a few hundred samples like this, some of the structure is actually consistent across pursuer samples. So now, like, so there's a question here, which drives us crazy, which is we're sampling from an approximation of the posterior, not the exact posterior. Which comes from a caveat of what we do. And so like it drives us mad, right? Because if we're sampling from a true honest to God posterior, then this is it. Okay, this is kind of like, yeah, there's probably is, I mean, according to our prior beliefs, there's structure there that you should be able to resolve if you had a bigger ALMA. But it's an approximation, so you know, probably, I don't know. But we're starting to see these things now, like so much fun because you're able to peer like and look at these residuals. Okay, they're not perfect. There's still signal in there. You know? And I don't see many people in interferometry, you know, publishing their residuals, which, you know, well, if you have solution like clean, I can understand why. Like these things is probably like, you know, red and blue all over, right? But here we're actually like solving down to noise most of the visibilities. So it's kind of interesting. I mean, not perfect.
This is fantastic. Yeah. Yeah. Really cool stuff.
Okay. Stop sharing.
Cool. All right. Unless anyone else has any quick questions, it's probably about time we wrapped up. Yeah.
I don't want to keep things going too long, so obviously we can move this to another chat next time we chat. But on the practical side of things, with sometimes your data samples are discrete, right? So for example, images, you said you were working with HDR images before. If you're trying to learn the score of that, but like the underlying distribution of possible images is continuous, whereas the samples you feed it might be discrete. Is that a problem? Is that something you need to consider?
That's a big problem. You just hit like, okay, so like diffusion is still very new. Like, so there are some papers that try to do discrete diffusion. We've tried them. They don't work super well. Still open question. Can you do that? I mean, there's a lot of caveat that you hit, right? Like I showed you 2 problems where I have amazing results, but the real problems that I want to apply this to, it's been unsolved for 2 years how you do it, because I need a forward model that's linear. Except like most problems that interest me have a non-linear forward model. Like you have those in interferometry. Like as soon as you want to, instead of like, as soon as your phase is out and you have to use your closure phases, oops, it's non-linear. You can't use that. You can't use the diffusion models, or you can try, but the approximation is going to be even worse than before. So like, there's a bunch like, you know, and people are working on these problems. I mean, I find like it's so interesting to work on these because I've been studying this. You know, you can study stochastic differential equation for a year and you're still not like even 10% through like what you have to know to understand stochastic differential equation. Like it's crazy. So, but having said that, applying these things in practice, learning a score network, very easy. Okay, it's very easy. It's kind of like just a few lines of codes, just make a fat neural network and train it on a big GPU.
Yep. All right. Sounds good.
All right.
Cool. All right, we should probably let Alex get to bed. It is kind of late over there, so
You know, from my timeline, I was supposed to be in the middle of my
oh, that's true, actually. Yeah. Sort of make sure you get a good sleep, you know, so you can keep up the good work.
Yeah.
Cool.
All right.
Yeah, well, I just want to thank Alex again. This has been really awesome. I really appreciate this. It's been really informative, and yeah, I'm sure this is going to stimulate lots of further discussion, and people will probably reach out and be like, "Can you help me with these diffusion model ideas I've had now?" So,
Okay,
yeah.
so I'm gonna link I'm gonna link my package now in the chat so you guys can just take it. But I have like if you just read the README on that, you're gonna get started in like 3 lines of code, roughly speaking. And I'm refactoring the code such that it's gonna have like a